go from the current slide, and it will come up one of these days, I think. Maybe not. Let me try it again. There it goes. Okay. Let me make this one announcement while the projector is trying to come on, and so far is having trouble. You know what next Tuesday is, right? Election day. We're going to be voting, aren't we? Okay, make your plans to, yes, please do. Are you not 18? Oh, okay, sorry. Okay, but as soon as you get 18, register to vote, okay? One of the most important things you can do as a citizen. I can't think of many other more important things that you can do as a citizen. And for some reason, this is not wanting to, there we go. I guess something was touching it in the back. All right, here's Lexi. Here's Seth. And here's Emily. All right. Anyone else come in since I called roll? Okay. Okay, I got you. Okay. So please, folks, remember, don't just put it and say, oh yeah, I'll vote. Make a plan. Like, for me, I teach on Tuesday and Thursday until 7:45. There's no way I can vote on the way home because polls close at 7. So that means I have to make sure I'm at the polls as soon after 7 o'clock, if not before 7 o'clock in the morning as possible, so I can get voted and get out here for my first class at 8:30. I think I can do that with no problem, but don't leave it to chance. Plan your day, how you're going to get to the polls and vote. And please vote. Everybody. Okay. All right. Any questions on anything we've done so far? None? Okay. Starting a new module today. This is module 13. And if my memory's right, after 13 we have 14. And after 14, I think that's it. We may, if we have some time at the end, introduce a little bit of functions to you. You won't be held responsible for it, but that way you'll have a jump on Math 112 when you get there. That's only if we have time at the end. But today we're starting Module 13. And it seems like we were making pretty good progress. This is the first time I've taught this book, and usually things don't go so well the first time I teach a new book. This time it seems to be moving along at a decent pace. All right. To me, that's flickering. Is it to you? Okay. Sorry. I can't do anything about that, so hope the bulb's not going bad. All right. Rational exponents and radicals. Now, what in the world does rational mean? Ratio, exactly. That's something divided, fractional type form. But where is this? In our exponents. Okay? And that's going to take on a whole new meaning. I'm assuming that most of you have had something like this before, but if you haven't, it's kind of a new concept. Now, what are radicals? These people that go out and protest all the time? No, well, that's one kind, but what are we talking about here? Say again? What do we mean by radicals? Give an example. Okay. Let's see. I see this here. Okay. Radicals are basically roots. Square roots, cube roots, fourth roots, sixth roots, whatever. Okay? So that's what this module is going to be addressing. Okay? And here's Ariana. All right. Anyone else? Okay. All right. So section 3.1 is going to introduce you to radical expressions. Like, well, never mind. We won't go into any radical expressions. And objective 13.1a is to simplify numerical. We're going to start with the numbers. Later we'll go to algebraic expressions. So we'll start with simplifying numerical radical expressions. A lot of coals in there, aren't there? Okay. Now, most of you are familiar, I'm sure all of you are, with what we mean by a square root. Okay? Square root of a positive number x. Now, why do I say positive number x? You cannot take the square root of a negative number, ever. And not just the square root, any even root. Now, we won't get into that yet, but that'll be the case too. You can only take square roots of positive numbers. So a square root of a positive number, x, is a number whose square is x. Okay? So in other words, if you have x under the radical, the square root of that is a number when you square it, you get x. It's the inverse operation, basically. A square root of 16 is square root of 16? 4. Okay? Is that the only square root of 16?
No.
Say again?
No.
No, why not?
Negative 4
will work too, because when you square 4, you get 16, but you square negative 4, and you also get 16. Okay? So the square root of 16 is both 4 and negative 4. All right. Well, this is a little different from most of our other operations. Other operations, you do something to that, you expect one result. Okay? Here, you can get 2 results. Okay? But you can only take square roots of positive numbers. You can't take them of negative numbers. So, okay. Every positive number has 2 square roots. Okay? One positive and one negative. And the symbol, that's the radical symbol, it's called the radical sign. It's used to indicate the positive or principal square root. So if you see this radical sign without a sign in front of it, that means the principal or the positive square root. Okay? So when you see square root of 16, not the words, square root of 16, that's only 4, not negative 4. Okay? If you see plus or minus square root of 16, then that would be plus or minus 4. Square root of 25, 5. Okay? The number or variable expression under the radical sign is called the radicand. So what's inside the radical is the radicand. The radical sign itself, or symbol, is that thing that sort of looks like a division, but it's not quite. Now, we'll get to it later. I want to say something else now, but we'll get to it later. The square of an integer is a perfect square. Okay? And I think you know most of these, right? 49 is a perfect square. Perfect square of what? Yeah, plus or minus 7. 81. Plus or minus 9. 144. Yeah, plus or minus 12. They're all examples of perfect squares. Now, the principal square root of a perfect square integer is the positive integer. The principal square root. And there is Q. Okay. Anyone else come in when I was looking? Okay. So the chart below shows square roots of some of the perfect squares, and they did leave one off, not much of one. Square root of 0 is 0. Okay, square root of 1 is 1. Now this is when you have principal square roots. Square root of 4, 9, 16, 25, 36, 49, we already did, 80, 64, 8, 100, 121, 11, and 144 is 12. I don't know who did it. It's only been recently, but in the room next door, there's a clock in front of the classroom. And somebody did this. It's sort of corny, but they put, for the hours, square root of 1, square root of 4, square root of 5, and they've got those all around the face of the clock. Well, have to cover the clock when you're giving a test. No, I'm just kidding. Okay. All right. Any questions on that? Dealing now with numerical radical expressions. Got it? Okay. If an integer is not a perfect square, its square root can only be approximated with numbers. If you write it with the radical, that's an exact answer. But if you try to write out a decimal form, you'll never get an exact answer. For example, 2 and 7 are not perfect squares. Square root of 2 is what we call an irrational number. Completely irrational. Square root of 7, irrational. Not just those two. Square root of 3 is irrational. Square root of 5 is irrational. Square root of 6 is irrational. Square root of 8 is irrational. Square root of 10 is irrational. There's a bunch of irrational numbers there. And that's just the square roots. You can then do the cube roots of a lot of those, and they're irrational. Okay? The decimal representations never terminate, meaning end, nor do they repeat. Okay? For example, square root of 2, it starts off like it might be a pattern, right? 1.414. Until you get to the next digits, and they go on and on and on and on and on and on, and never, ever repeat any pattern whatsoever. Ever. Even when Drew comes in. Okay. Anyone else come in since I called off? Okay. Square root of 7, even worse. 2.6457513, blah, 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 and you just keep going and going and going. You'll never, ever see a pattern emerging. Okay? That's what makes them irrational numbers. If they ever started repeating, like 6457, 6457, 6457, 64, that would be a pattern. Or 2.6457513131313, that would be a pattern. Okay? There's never a pattern. Okay? The radical expressions contain radicands that are not perfect squares are generally written in simplest form. And what do we mean by that? Radical expression in simplest form when the radicand contains no factor greater than 1, of course, because 1's always there, that is a perfect square. Okay? So that's the first thing we're going to look for in a radical, the radicand. Are there any hidden perfect squares in there? If there are, factor them out and take those roots out of there. Okay? So the property of square roots is used to simplify radical expressions. Okay? If A and B are both positive real numbers, then the square root of AB is simply the square root of A times the square root of B. This is how we pull those perfect squares out. So if you see a number inside a radical and you see it contains a factor of 4 or 9 or 36 or whatever, then split that out from the other, and the square root of 36 would be 6. So that becomes a 6 times the square root of whatever is left. That's what we mean by simplifying a radical expression. Yeah, like I just did, square root of 36. Okay. Yeah, in fact, I think one's coming up right now. Let me check and see. If not, we'll be doing the ones right there. Okay. Actually, we will do the ones right there. Okay. Let me mark Sierra here. All right. Does anyone else come in since the call roll? Okay. All right. If you're got your text or ebook or whatever, this is on Module 13, page 3. Okay. And it tells you to simplify a few forms. Okay. And let me get my pen set up. Okay. The first of these is the square root of 72. Now, first thing to do, in fact, not the only thing to do, to simplify a radical is see if you can find, okay, this is a square root, so we're looking for perfect squares hidden in 72. Now, you know your perfect squares, right? Forget about 1. It's always there, okay? Is 4 a factor of 72? What you think? I think not, is it? Second? No, it will. 4 going to 72 how many times? 18 times, okay? So sure enough it is. So let's factor out of 4. Square root of 4, just like we did up here, times the square root of 18. Okay? 4 is a perfect square. We could take that square root. How about 18? Are there any other perfect squares hiding in 18? Say again? 9 is in there. So let's factor out a 9. And maybe I should have done this. I'll do it this time. Square root of 4 times the square root of 2 times 9, which would then be the square root of 4, times the square root of 9 times the square root of 2. Now this is really dragging it out, folks. What's the square root of 4? 2. Square root of 9? 3. Square root of 2. So this is what's 2 times 3? 2 times 3? 6 times the square root of 2. Okay. Now, that's one way to do the problem. Or you can get Ron to do it for you. Okay. You see it now. Okay. Here would have been slightly simpler if any of you would have seen this, but none of you answered, so I started going through the simple way. Okay. Looking at 72, if any of you happen to notice, that is the square root of, that is 36 times 2. And what's the square root of 36? 6. 6 times root 2. You could have done it in one step there, basically, if you had seen that. If not, go through all your perfect squares. 4, 9, 16, go through them all until you got down to something you know doesn't contain a perfect square. Does that make sense? And Ariana, is that what you meant by illustration with numbers? Okay. All right. Then if that's so, let's do another one. Okay. The square root of 360. Anyone want to hazard a guess of whether there might be a perfect square lingering, hiding somewhere in 360? What you think? Say again? 36 is in there. So that's going to be the square root of 36 times the square root of what? What's left when you factor out of 36? 10. Okay. What's the square root of 36? 6. Okay. Are there any perfect squares lingering or hiding or something in 10? No. 10 is 2 times 5. No perfect squares in there. Right? So your answer is 6 times root 10. Okay. Now that's one way to do this. Okay? Look for those perfect squares. Let me show you another way that's usually not that helpful when you're doing square roots. But later when we do cube roots and fourth roots and eighth roots or whatever, it may be very helpful. Let's take this 360. Now this is the long way. But let's take the 360 and do a prime factorization of it. What's the smallest prime number that will go in the 360? 2. 2 times what? 180. What's the smallest prime number will go in the 180? 2 times 90. What's the smallest prime number will go in the 90? 2 times... Say again? 45. Smallest prime number will go into 45. Okay, 5 will go into it. Okay, yeah, okay. And 3, and 3. Exactly. We didn't quite get them in order, but it's okay. Because, let's see, let's do this simply. This is 10 times 9 would be 90, times 4 is 360. Yeah. We got all the prime factors. Okay? Now, here's what you do. Since this is a square root, you find all your pairs. There's a pair. Don't look for apples, only pairs. Okay, no. And there's a pair. Right? Those can come out. So that would be 2 times 3. And then what do you have left? 2 times 5 is 10. There you have it. 6 root 10. Now again, most of the time for square roots, you'll see these perfect squares easier than doing this. But if you don't see them, you can always do that. Do a prime factorization, and then since it's a square root, pull out pairs. See, 5's not in a pair, and this 2, since those 2 were taken, is not got a pair either. So leave that as 2 times 5 is 10. Does that make sense? And when you pull them out, they're no longer in the radical. I don't know how many students I have that will then turn this into a radical 6. No, it's not. That's set. It's outside the radical. You pulled out the square root. Okay? So, and that's sort of why I like that method a little bit better. Okay? Want to do one more? Yes?
If we were to leave 2 times 3 to the square root of 10, would that be correct?
Okay, a little while.
If we were to leave 2 times 3 to the square root of 10, would that still be counted right over this? Or do you want it?
You're making me do your multiplication for you. Is that what you're saying? Okay? As if I don't have enough to do, huh? Okay, no, you want to do it. I probably wouldn't take off points, but I'd write it down and say, hey, you know that. You know, but yeah. No, if you carry it out, that's try to go on and multiply. Just like, now, if you don't reduce a fraction to the lowest terms, you're going to lose a point. You know, I don't know if I'd charge you a point for that, but try to take it as far as you can. Okay, let's do one more. Let me just sort of put this in the middle of the page here. The square root of negative 16. What's that? Anybody? Say again? Okay, I heard a negative 4. Okay? Now, how do I check that? If I've taken the square root to get this, how do I go from here to here? You square it. No, not square root. Square it. A square undoes a square root, right? Like multiplication undoes division, addition undoes subtraction.
That would be 16.
That would be 16, not minus 16. Guess what, team? You can only take square roots of positive numbers. No solution. This is not right. No solution. Okay? You cannot take the square root of a negative number. Now, just looking a little bit ahead, once I mark Saya here, find him. I know you're in here. There you are. Okay. Just looking a little bit ahead, if this were a cube root, you can take cube roots of negative numbers. Perfectly fine. Because a negative times a negative times a negative is a negative. So you can't take a cube root. But a negative times a negative is a positive, so you can only take square roots of positive. No solution on that. Okay. Good deal. Okay. Now, the way they answer it, they say, not a real number. Okay? And later, you'll learn, when you get to Math 112, say, that there are not real numbers, but imaginary numbers. Really. And that would have to have an imaginary solution. Or at least an imaginary part. We call those numbers complex numbers. They have real and imaginary parts. All right. So I think now we're ready for the focus. And here's the focus. Okay? Simplify that. Now you can use any method you want to, as long as it's right. What method would you like to use? Prime factorization? Why not? What's the smallest prime number going to 252? 2 times what? Say again? 2 times what? 126. What's the smallest prime number going to 126? Pretty easy. 2. 2 times what? 126. Small, okay, 2 into that would be? 2 into 12 is? 63. Oops, okay, I didn't mean to write that. Sorry. 63. I meant just to say that, okay? What's the smallest prime number going to 63? Nope, 2 won't go into 63. That's an odd number. 3. What's the smallest prime, and what do you have left? 3 into 63 is? 21. Smallest prime number going to 21. 3. Well, what's left? Is that prime? Yes. So we're done, I think. Okay, let's just make sure. 4 times 9, 36. Yeah, I believe that's right. Okay, and since we're doing square roots, what do we pair up? Aha. I gave it away. You look at your pairs. What pairs do you see there? And 2 times 3 times root 7, and that would be 6 root 7. Okay. Yeah. Highly. Okay. Is anyone else coming since I called it? Okay. Make sure. Yeah. Looks right. Okay. Now, any questions about that? Did you want to try it another way? The other way I would do, I like prime factorization, especially when you're doing other roots. This, if you got a calculator, just what are your perfect squares? Don't count 1. 4, will 4 go into that? You would see it would. And then next one would be 9. Yeah, it would go into it. So you can start doing it that way. But this works perfectly well. All right. Any questions on it? That's how we did it. Let's see how they did it. Okay. They started off, oh, yeah, they wrote the book. They knew what the answer was. They said, oh, yeah, 36 would go into that. I didn't know that. No way I would have realized 36 would go into that. Okay? But since they wrote the book, they knew what it was. Okay? So I like the way y'all did it. I think I would have started with 4. So will 4 go into that? Sure, it would. Okay? And then after that, I would see the others. I think. But they went right to 36. Don't expect yourself to do that. I wouldn't do it. I wouldn't think you would either, but you might if you're that good. Okay? So that'll be square root of 36 times square root of 7. And what's square root of 36? 6 times root 7. Perfect. Any questions on that? Does it make sense? All right, good deal. Let's see, I think that may be. There is a check your understanding. Please do that one as well. Okay? Now, that's the end of the section. However, there's another focus here that they didn't put on the slide set. So let's us do that. Simplify this. -3 on to root 90. Root 90 goes through, no, it doesn't. Okay. Okay. What would you suggest we do on that? You have a couple of options. How would you approach it? Say again? No, you may have said it right. I just can't hear. Try it. See if it's a perfect square. You may just plug it into your computer. Why not? Give it a shot. You'll find it's not. Okay? So now we start doing what? Say again? Okay, you like prime factorization? Perfectly fine. The -3 is still there, folks. Don't throw it away. And what's the smallest prime number will go into 90? 2 times what? 45. Smallest prime number will go into 45. Or any prime number will go into 45. 3 will go into 45 how many times? 15. Smallest prime number will go into 15. 3 times what? 5 is 5 prime? Yes, it is. What's the only perfect square you find in there? 3. Okay? That would have been the 9 up here. Okay? So that's -3. That's out front. Times 3. That's from pulling this out. Times what? Square root of 10. Perfect. So this will be Bree negative 9 root 10. Okay, there we have it. Okay, and if you look in the book, you'll see that's the solution they give. Please do your check your understanding too. Okay, and then you have 4 practice problems. Please do those. Now, I'm sorry the book doesn't give you more practice. They have the check your understandings and the practice problems, not that many. So please do them. Please do them all. All the answers are at the end of the module, so check them out. Find that, okay? Now, that's one reason the other instructors, once teaching from this book, said, get us a new book, okay? These don't have enough example or practice problems. So we're going next term with a new edition, with a different book from this one. However, this book will still be used for Math 100 next term only. Beginning in the summer, both 098 and 100 will go from the new book. But this spring, 098 will go from the new book, but 100 will go from the continuing this book. So you can still, if you need to, get rid of your book. There will be 098 students who will be looking. No, they probably already have the book. But if any new students come in, you can still, if you don't want to keep your book, get rid of it. Okay? So any questions on 13.1a? Okay? If not, all right. We will go to 13.1b. All right, and we'll go from current slide. Still doing Module 13, Rational Exponents and Radicals. Is still doing 13.1, which is Introduction to Radical Expressions. But now in 13.1b, we'll simplify variable radical expressions. Not numerical, variable radical expressions. And guess what? We're going to do the same type thing. That's one reason I introduced it to you before. Okay? So here we go. Variable expressions that contain radicals do not always represent real numbers, because you don't know if that variable is positive or negative. So you don't know. The variable expression shown below does not represent a real number when x is a negative number, such as 4. The square root of x cubed. You can't guarantee me that variable can't be a negative 4 or negative 1 or negative anything. If it is, then this is undefined. No real solution, okay? Not a real number. But what we're going to do is assume that what's in here, they'll tell you this in a minute, are always represent real numbers, okay? So what we'll do is just treat it as if whatever the variables are will work, okay? We won't deal with those that don't work, okay? Okay. All right. So, what in the world is the square root of a squared? That should be fairly simple. For any real number a, notice we're not saying only positive, for any real number a, the square root of a squared, guess what? This undoes that. So you should get a. However, because it could be a plus or minus, we put absolute value of a. You see, a could have been a negative 7, but negative 7 squared is 49. Square root of 49 is 7, not negative 7. So that's why we put the absolute value bars. That guarantees it always has an answer. So if a is greater than or equal to 0, meaning a positive number, then this is always a. The square root undoes the square, and you wind up with a. Anytime a is positive. Okay? So what's the square root of 5 squared? What's the square root of 9 squared? 9. Okay, that's pretty easy. Okay. Now these are variables. We're back to numbers here. A variable of a product of variables, written in exponential form, is a perfect square when each exponent is an even number. So if that's a square there, perfectly fine. If that was a 16, perfectly fine. If that was a 3 there, not quite perfectly fine. You can still simplify it, but it won't be just an even number. Okay. A whole number, let me put it that way. Okay? A variable radical expression is not in simplest form when the radicand, that's the inside of the radical, contains a factor greater than 1 that is a perfect square. Those include variable factors as well. Okay? The same rule as before, only now we're dealing with variables. Now let's see if they had any before this. Yes, they did. So let's go back. Yuck. That probably has the most white space, so let's do it. Okay, it'll come back, I think. There we go. Okay. So let's simplify this. Let me get my pen back. All right. The square root of a to the 6th. How would you do this? Okay. Now, they left off on the slides. I'm going to go up and read a paragraph to you, part of a paragraph. In order to avoid variable expressions that do not represent real numbers, and so the absolute value signs are not needed for certain expressions, the variables in this module, Module 13, will represent positive numbers unless otherwise noted. So we're always assuming the a's are positive now, so we don't have to worry about absolute values. Okay? So, how do we do the square root of a 6th? Okay? Kind of, but it's even easier to do. What's your favorite technique? Okay, let's factor it. Okay? The square root, and what is a to the 6th? A times, a times, a times, a times, a times, a. 6 factors of a, right? And then what did we do before? Since this is a square root, we pair them. There we have it, just like we did with numbers. Why put numbers in there when we can use letters, huh? Okay. So what do we have? A cubed. Perfect, perfect, perfect. A times A times A. Because every pair comes out as an A. Got it? Make sense? Okay. There's going to be another way that makes it really easy too, but they haven't told us that one yet. We just can't wait to get to that one, can we? Okay. But you see what we're doing? Just like we did with numbers, just factor them out there, and then any pair you pull out, that first one would be an A, then the next one would be an A, so A times A. Next one would be an A times A times A, that's A cubed. Right? Does that make sense? All right. How about this one? The square root of x to the 7th. Okay. Now, what will that be? That's a 7. That's an ugly, ugly 7. Okay, let's see if I can make it a little nicer. Okay. So how would you approach this one? That's not an A. X times X times X times X times X times X times. One more. Okay. All right. And then what do we do? Pair them up. Whoa! What happens here? X cubed times the square root of x. Right. Perfect. Way to go. Okay? x cubed times the square root of x. Okay. Make sense? Now, I think what I almost heard someone doing, and that was pretty clever, is say that square root of x to the 7th was equal to the square root of x times the square root of x to the 6th. Was someone thinking that? It makes sense, right? And we already know what square root of x to the 6th is. X cubed times the square root of x. So there's another way if you don't want to write them all out there. I'll show you another way later once we get the other nomenclature or technique down how you can do that. Okay? Does this make sense so far? All right. Now, those are so easy. Let's do some that are a little more challenging, like 3x times 8 times the square root of 8x cubed y 13th. I made my radical a little too long, but don't forget your 3x. It's in there, right? 3x. Now, what are you going to do next? Now, this is just one way to do it. You can do it other ways if you want to. How would you approach it? Y13. Yeah, y to the 13th, right. This is going to get pretty long writing them all out there, but we can do it, can't we? Or not. If you think of a shorter way, we can do that. So how would you approach it? Anybody? What would you do?
I would factor out the 8x to the 3rd.
Okay, well, how do you factor 8? 2 times 4. That would be fine. I'm going to write it that way since you said it. Perfectly fine. Next, times x times x. Okay, that's perfectly fine. Oh, this is going to take a while, I'm afraid. What will this be? Okay. Yeah, easy enough for you to say. Y times y times y times y times y. 1, 2, 3, 4, 5 times y times y times y times y. 1, 2, 3, 4, 5, 6, 7, 8, 9 times y times y times y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All that's under the radical, folks. Okay, has anyone thought of an easier way?
Yeah, I just did y to the 12th and had a...
Very good. Just like we did 2 times 4 is 8. You could have done x cubed is x times x squared. And you could have done y to the 13th is y times y to the 12th. Okay, I like it, but since we already started, let's see what we got. The 3x is there. Now what do we look for? Perfect squares. There's a perfect square. What's that a perfect square of? 2. Pull it out. Gone. Next. X times x is a perfect square. Pull that out. X. Gone. Okay, next. There's a pair, 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 and no apples. How many we got? 1, 2, 3, 4, 5, 6. Y to the 6. And what do we have left under the radical? 2xy. You see it? Yeah, go back and check them all. So you've already hit on a good idea. If this is an odd number, pull out 1, then it's going to be an even number. And then guess what? You take half off. It goes on the outside. Good observation. You're thinking math well. Ooh, lucky Halloween. Okay. Make sense? All right. Oh, we can clean up the answer a little bit, can't we? What will that be? Or Bree wants to leave it like this, but 2 times 3 is 6. X times x is x squared. Y 6 times the square root of 2xy. All right, let's see if that's what they got. 6x squared y6 times the square root of 2xy. Way to go, team. You did it. Okay? Does that make sense? All right, good deal. All right, to move along. All right, now we get to do our focus here. So focus, people. Okay. How would you do this first one? The square root of 24x to the 5th. You tell me. There's several ways you can approach it. Anybody? Say again? 8 and 3? Is 8 a perfect square? No, neither is 3. Ah, 6 and 4. That would work. So let's do square root of 6, square root of 4. Okay, because 4 is a perfect square, 6 is not. Okay, and how about next? How about the x's? Say again?
Yeah, we know we're going to have x to the 4th outside of the
Okay, x times x to the 4th. Very good. Is that what you meant? I thought it was. Okay. So you split up 24 into its perfect square, 4 times whatever's left, 6. And then x to the 5th into its perfect square, x to the 4th times whatever else is left, 6. Okay? Pull out the perfect squares. What's that? Perfect square of 4 is 2. Pull it out. Perfect square of x to the 4th is x squared. Okay? And then what's left under the radical? See, those are gone. 6x. 6x. Okay, got it. Okay. Make sense? Good deal. Ooh. How about this next one? What do you write first? Anybody? Yeah, get the 2a out there. Don't forget it. The square root of. Now we look for what? Perfect squares. Okay, do you see any perfect squares in 18? Oh, wow, that's a new one. I had forgotten that. What's that? Yeah, that's 16, not 18. Okay, sorry. Any perfect squares in 18? Let's go through our perfect squares. Don't count one. Is 2 in there? No. It's perfect square of 3. Is that in there? Yes, 9 times 2. So we'll do a 9 times 2, right? All right, next. A times a squared. Perfect. Okay, next. B to the 10th is perfectly fine, just like it is, okay? So, any perfect squares you see? There's a 3 there. There's an A there. Any others? B to the 5th, you got it. So it'd be a 2A that we already had, times 3 from the 9, it's gone, times A from the A square, it's gone, and times what? B to the 5th, it's gone. And what's left under the radical? 2A. Perfect. Now, Bree, we clean this up a little bit. What does that give us? Say again? Okay. Yeah, 6. A squared. B to the 5th. On to radical 2A. Perfect. Way to go, team. Y'all are good at this. Make sense? A little bit. Okay. All right. Let's see what they did. 6A squared B 5th radical 2A. Good for them. Okay? Yeah. All right. I'm going to erase what I did, if that's okay. Or people still writing? Or sleeping or something? Okay. Everybody got it? Okay. Then I'll erase what I did, and we'll see what they did, which probably is going to be fairly close. Let's see what they did. All right. They started with the first one, square root of 24x to the fifth. And boy, they were clever, weren't they? They pulled out all the perfect squares. I like the way y'all did it. It was a little bit better. 24 is 4 times 6. I would have done that separately. And then this is x times x to the fourth. X times x to the fourth. They were so clever, they knew the answer. They wrote the book, right? Okay. What's the square root of 4x to the fourth? 2x squared. If you do it this way. I don't recommend it, but if you see it that way, by all means do it. So that's going to be, split them up. Okay, I would take an extra step to do that. Yeah, no problem with it. And that would be 2x squared times the radical square root of 6x. All right, same answer we got. It went about it a little bit differently, but still got the same answer, right? So let's go to the next one. Everybody got it? Okay. Then we go to this one. Okay, the 2a stays out here, and they split out the 9, the a squared, and the b tenth all together. You don't have to, but you could. What's left from here is a 2. What's left from here is an a, and you used all of the b's, so you only have that. So if you see this better and makes more sense, you can do it this way. I like it the way y'all did it. First doing the numbers, then doing the a's, then doing the b's. But you can do it this way if you like. If you see it all at once, go for it. It's kind of like when you read. If you read word by word by word, that's certainly there. Or some people read phrases together or lines together, and some speed readers just sort of, I don't know how they do it, but they read the whole paragraph. I don't know. I don't do it that way. Okay, but anyway. So anyway, on this one, there will be 2a times the square root of 9, the perfect square part, 9a squared b 10, times the square root of whatever's left, 2a, and that would then be 2a times 3a b to the fifth times the square root of 2a, and then you multiply your numbers and variables together, and it gives you 6a squared b fifth times the square root of 2a. Perfect. Make sense? All right. That was check yourself, no, what do they call this? Focus, and that followed by check your understanding 3. So please do those as soon as you can after class. Okay? Now, they don't do any more, but in the text you have another focus. So whoa, why would they leave off this one that looks like it's so much fun? They leave the fun ones off, you know, they just do the simple ones, okay? So let's do the fun ones. The square root of 16 times x plus 5 squared. Say again? Yes, absolutely. It undoes the square, you might say. So what would you do? How would you approach it?
We would just have 16 times x to the fifth. Times x plus 5, right? Left.
Okay, close. You left the 16 as a perfect square. 4 times x plus 5. Okay? If you see that, go straight for it. Okay? But if not, that's the square root of 16, which is 4. If you write it out, you'll probably catch that. And square root of x squared plus x plus 5 squared is x plus 5.
Can you simplify it?
Now simplify, exactly. And what would that be? 4x plus 20. I never know whether they're going to do that next step or not. You can or not. I wouldn't count it wrong either one of those answers you left. But let's see how they do it. Yeah, they do that and then distribute as well. Perfectly fine. Okay? Then there's a check your understanding 4. Please do that one. And then there are 6 practice problems. They gave us a few more this time, so please do all 6. All right, any questions? Is this making sense? Okay. Yeah. Anything you're not certain about, please ask. See, when I give you quizzes, I want them all to be hundreds. They're easy to grade that way. So I want you to ask all your questions now and not get them wrong later, okay? Make my life easy, okay? Okay? Do you want to either do the check your understanding or one of the practice problems? You name it. Name it and claim it. Practice problem. Okay, you want one more like this one? Okay, how about practice problem number 6? Is that okay? Okay, practice problem number 6 is the square root of 9. This is practice problem 6. Okay, this is module 13, page 6. Okay, square root of 9 times x plus 2 squared. Second? That's it. 3, because the square root of 9 is 3, times x plus 2, because the square root of a square is the thing. And then you can take it another step if you want to and make it 3x plus 6. Okay? Yep, that's what they got to. Good deal. Any other questions? Yes?
Can we do another one like the one before the last 2?
Sort of like the one at the top there? Okay, you want check your understanding or practice? Okay, let's go back to check your understanding 3. You want one of each or one of the harder ones? Okay. So check your understanding 3 would be 3a times the square root of 28 a 9th b 18th. Okay. That's check your understanding 3b. Oh, yeah, a to the 9th. You got it. Yeah, sorry. Making fun of my writing. It's okay. I'm not hurt by it at all. Okay. How would you begin? Okay, 3a is there, so don't forget it. You're absolutely right. Four times 7. 28 is 4 times 7. 4 is a perfect square. I like it. Next. A times a to the 8th. Perfect. Times b to the 18th. Y'all are good. Okay. The 3a's out there. Don't forget about it. Okay. Anything come out to join it? Times 2 from the 4 there, that goes out. A to the 4th comes out. And b to the 9th comes out. Okay, and what are you left with under the radical? 7a. Okay, clean it up just a little bit more, and that would be 6. A what? 5th, got it. B to the 9th times the square root of 7a. Nothing more you can do than that. And let's see. 6a to the 5th, b to the 9th, square root of 7a. Perfect. Way to go. Any other questions? Need to see any more? Way to go. All right. Now, what sort of bugs me a little bit is they made all this kind of problem as if it's perfect square, perfect square. Guess what? You could have a 32 here that you could have to factor, and you could have an x plus 5th to the 5th power. And take 2 of them out, leave 1 in. You can still do that with this. You don't have to have them perfect under here, just like you had them here. They didn't have to be absolutely perfect squares. Okay. Just get that straight. The odds are they're going to wait and do that to you on the quiz. Okay, right? You know, not going to show you how to do it here, but wait and do it on the quiz. Okay, they wouldn't do that with it. All right. I think that ends 13 1B or whatever it was. Okay, so there we go. All right, we'll discard that and end that and move on to 13.2a. All right. Now, as soon as we finish simplifying expressions, why not let's go and add expressions. So we're still in Module 13, rational exponents and radicals. Okay? We're in 13.2 now, which is addition and subtraction of radical expressions. Now, what things can we add in general? If these were terms, what would they be? Like terms. And like terms meaning they have the same variables, right? Different coefficients, but same variables. Well, here you have radicals. They have to have the same radicals. So let's see if that's what's going to happen. 13.2a, okay, the first part here, we'll add and subtract radical expressions. That's where we're beginning. I thought we were going to do numerically, but let's see if they do. Yeah, they're going to start numerical, okay? Okay. The distributive property is used to simplify the sum or difference of radical expressions with the same radical hand. When you're adding 5 root 2 to 3 root 2, can you do that? Yeah, what would that be? 8 root 2, exactly. Okay? Factor out the root 2. Think of that as a common variable. But it's not a variable, it's a number. So factor that out, and then 5 plus 3, 8 root 2. That makes sense. Now, if that was 5 root 2 plus 3 root 7, no, you can't combine those because they're not like. The radicals are not alike. Okay? And that's what they're saying here. Radical expressions are in simplest form and have different radicands, cannot be simplified with the strip. If they have different radicands, not. Like 2 root 3 plus 4 root 2, there's nothing you can do to simplify. That's already as simple as you can get. Okay? Because these are not the same, nothing's the same. Okay? So they cannot be simplified. Only if they have the same radical. To simplify the sum or difference of radical expressions, simplify each term. Then use the distributive property. What do they mean by that? Well, I think they're probably going to show us first, and then we'll do the focus. So let's back up and do it here. Let's do a subtraction here. Whoops, let me get my pen back. Okay. 4 root 8 minus 10 root 2. What would be your first inclination here? Okay. See if you can simplify this and find something in common. Because guess what? The 10 root 2 is simplified. 4 root 8 is not, is it? There is a lingering or malingering, one or the other, perfect square in 8. What is it? 2 times 4 minus 10 root 2. Don't forget about that. Now, what can you do with that? Okay, 4 times the square root of 2 times the square root of 4 minus 10 root 2. Now, I'm dragging this out, but, you know, after a while you might be able to skip some steps. You see what you can do? Root 4 is 2. So this will be 4 times 2 times root 2 minus 10 root 2. Now what's 4 times 2? And this time you've got to multiply these out, Bree, okay? That would be 8 root 2 minus 10 root 2. How did I get a 10 under there? I think Seth did that while I wasn't looking. Okay. Okay. All right. And what will this do? Negative 2 root 2. Perfect. So don't look at that and say, oh, different radicals you can't simplify. No. Simplify the radicals first, then see if you can simplify. Okay, always pull out, the first step, always pull out perfect squares or cubes or whatever the root is. Okay, let's see if that's what they got. Look at them, they got it right. -2 root 2. Make sense? Yeah, if you get common radicals. See, these don't have common radicals to begin with, but when you simplify that, now they do have common radicals, so now you can add or subtract or whatever. Yeah, perfect. Okay? What's that? Yeah, we are, as soon as everybody finishes writing this one. Everybody got it? Okay. So let's move to the first focus. And it'll actually have 2 of them. All right? Let's do with the first one first. Oh, man, what a piece of cake, huh? What is this? A little louder? 14 root 2. Perfect. Okay? Now, you can do it any way you want to. You can go straightforward brute force method. 5 minus 3 is 2, plus 12 is 14. Or add your positives together, 17 minus 3 is 14. But they got the common radicals, so that was easy. Boy, piece of cake, right? Makes me hungry. Okay. How about the next one, though? Uh-oh. Not common radical, can't simplify, is that right? No, we got to do some work first, right? Don't forget the 3. What do we do next? Second, 3 times 4. Square root of 3 times the square root of 4. Perfect. Minus 5. Don't forget the 5. Anything here? Oh, 5 times 5. New math. Okay, I forget these, okay? Nine times 3, square root of 9 times the square root of 3. So I sort of skipped a step there. Is that okay? Okay. Now, any perfect squares there? 2, that's a 2. So that'll be 3 times 2 times root 3 minus 5 times 3 root 3. And 2 times 3 is 6 root 3 minus 15 root 3, and that gives us -9 root 3. Perfect. Okay. 14 root 2 for the first one, -9 root 3 for the next one. See? I wish I could make this harder. I've tried, but I can't figure out any way to make it harder, so it's just pretty straightforward, isn't it? I'm just kidding. Okay. All right. Okay. All right, ready to go? All right, I'm going to erase what I did, so I won't muddy the water for them. Okay. And let's do the A one first. That was all distributing because you had like radicals everywhere. So 5 minus 3 plus 12 times root 2. And however you want to add those together, 5 minus 3 is 2 plus 12 is 14. Or 5 plus 12 is 17. Minus 3 is 14. However you do it, it comes out 14 root 2. Good deal. Okay? And it sounds like we must be running out of time. So let's get this one done quickly. 3 root 12 minus 5 root 27 is 3 root 4 times 3. 5 minus 5 root 9 times 3. And that's going to be 3 times root 4, which is, 5 times root 9, okay. That's be 3 times 2 root 3 minus 5 times 3 root 3. 6 root 3 minus 15 root 3, which is 6 minus 15 is 9, negative 9 root 3. Okay. There's a check your understanding with 2 on it. And then there's another focus. Let's see if, they don't do the other focus. So if, I'll probably come back and do this next time. Okay, we will start with, actually they have another sample first before they do a focus, so we'll start there next time. All right, any questions? Good deal. Have a good weekend, and of course, by the way, if I get a research paper in today, you still get 2 bonus points. If you wait until next week, it's down to 1 bonus point, because this is the last day of October, remember? Okay. Yeah. Quiz? Okay. Let me end this.